The topic of the video is harmonic perturbation in time dependent perturbation theory. If you take the perturbation Hamiltonian h sub p of t as 2 times h sub p0, which is a constant, and then cos omega t, then the amplitude of transition, amplitude of the probability transition between state n and then state m is given by this a sub m 1 t as 1 over h cut into this integral. And if you substitute the value of s sub p from this expression here, so we can write this thing as 2 into h sub p0, and then the matrix element mn, and then cosine omega t as it is. But in the next step, I think we write the cosine omega t as e power I omega t plus e power minus I omega t all divided by 2. So we have this cancellation of these two and these two, so we'll get this integral for when we write e power I omega t into e power I omega mn t, then it will become this one. And then if you write this and this together, it will become e power minus I into omega minus omega mn t, and we can write the dt outside. So if you do the integration for this term and this term, and if you substitute even the limits, which are 0 and t, so we get this expression for our am1t. Here, in case if our omega was such a way that omega minus omega mn is equals to 0, then this second term will become dominant, because this denominator will almost tend to 0, so it will become infinity. So in that case, we see that em minus en will be h cut omega, and that's what will be the condition for absorption of light kind of thing, that is between the levels n and m. So we'll have a transition from level n to level m, where we'll have this energy h cut omega, which looks like the energy of a photon getting absorbed between these limits, between these energy levels. But if you have the condition omega plus omega sub mn is equals to 0, then we see the first term actually dominates. That's because in the first term we'll have the denominator being equal to 0, so it will kind of explode. So in that case, we'll see that em minus en is equals to minus h cut omega, and if you rearrange this, we'll see that en equal to em plus h cut omega. So this will be the condition for transition of this system from level n to level m. So it is a condition for stimulated emission between the levels n and m. In case if omega mn plus omega is actually kind of far greater than omega mn minus omega modulus, then we can ignore the first term in the expression of am1t. So we can only take this, the second term, which is for the absorption of light. So in that case, we can write down am1t modulus square as 4 into h p0 sub mn modulus square divided by h cut square into sine square omega mn minus omega divided by 2 into t all divided by omega mn minus omega square. And in this case also, we can define the transition probability that is between level n to some continuous energy levels m. Then yeah, we can define it that way, and mathematically it is actually equal to 1 by t into summation of all probabilities between the energy level n and m. So we can write this thing as modulus square of am1t. And for continuous energy levels em, between the energies em and em plus dem with the density of the states as rho em. The number of states can be written as dem into the density rho em, and as they are continuous, then we should replace this summation with integral, so we get this expression. But from here, if we substitute for am1 t square, then we'll get this big thing here. And if you assume that rho em is actually kind of a slowly varying function of dE, or I mean, we can even express this dE as d omega mn into h cut. So so if you say that this rho is actually slowly varying function, then we can take this thing out of the integral, and then if you actually write dem as d omega mn into h cut, and then if you want to try to, if you try to write down this d omega mn as d omega mn minus omega by 2 into t by uh, into t, then we should actually divide this thing by t by 2 here, and then here in the denominator also, if you want to write omega mn minus omega by 2 into t, then here we should actually write 4 by t square. So here we'll have uh, uh, cancellation of 4 and 4 here, and then t square, this t and this t and this t square will go off. So ultimately you will get 2 into modulus h sub p mn square into the density of states divided by h cut, and then this integral whole thing will actually give you pi. So we get the probability, we get the transition probability W as 2 pi over h cut into modulus S sub p mn whole square into the density of states rho em. This also looks the same as we had for the case of the constant perturbation theory, the Fermi golden rule. So that's it in this video, and thanks for watching.